Woo! According to you, it's pretty much breakthrough, but I think it's the breakthrough because it's pretty much like group project. So thanks to she and from who I already. So yeah, just to recap a bit, right? Like Nova, right? It literally introduced us to folding scheme, which literally just folding R1CS, so that you don't need to like verify at each step, right? So you just fold it together and then you can verify at the end. And then we have supernova, right? Like we just talk about. So the nova is R1CS, but it just limited you to just perform one function. So even though you can do recursively, it's just the same function, right? It's just like f of f of f or x or something, right? But then supernova makes you able to like in each step you can either choose one, right? Let's say like one from the like set of like different function, right? So it's more flexible and it makes sense in EVM that has like different opcodes and everything. And then there's another papers coming before Protostar, which is hypernova, which basically like here both nova and supernova are limited to just R1CS. But then hypernova try to generalize that so that not just R1CS, you can do Plonk, you can do like custom gates that are degree, not just R1CS. And yeah, and here we are at Protostar, which is basically like group project. So it just like try to even like not only support all of this, but try to generalize that more. So what does that mean by like generalize it, right? So to talk about Protostar, I think there's there's two main things. The first thing is that it generalizes like what can be full. So again, those three dudes like R1CS and even though hypernova, it's also be able to do like Plonk or those stuff, right? But this generalizes it even more. So to understand like what things can it fold, I think we just like a bit recap about like three things that people in serial knowledge think about when like they prove something, right? Like the first thing is called completeness. So completeness means that like if you have a valid witness, the verifier will like pass, we approve of your proof, right? So like valid witness make verifier happy. Yeah. And then we have soundness, which basically means that like intuitively, if the verifier is pretty much like the opposite, like converse of this. Like if the verifier is happy, it means that like you have like valid witness, which means that like yeah, if the verifier has happy, like it means that you cannot just like fake like witness. And the way that if you guys read in the papers, if you have something called like extractor. So this is just the way to prove this like soundness statement, which basically means that like if the verifier is happy, which means they accept the proof, right? There will be an algorithm called extractor that can extract a witness out of the proof. So it can extract witness out of proof. And why does that mean that like no one can cheat? Because if you cheat, and even though like you get like accepted by verifier, people still can extract witness of it and can see if it's really the one that's it for. So basically like extractor just the proving, it's just the way to show that like this thing is sound, because if the verifier is happy, they can extract a witness, and if they cheat, they have a different like the wrong witness, they will just see that this witness is not really right. So and yeah, I mean you see this has nothing to do with zero knowledge, right? But in zero knowledge there's a like zero knowledge, which just basically mean that like when prover interact with like verifier, it doesn't leak any information, right? And yeah, like most of the stuff or everything that we like familiar with just like have these three properties. And yeah, the same goes for R1CS or Plonk or everything that Nova like try to make full of it, right? But then we try to generalize what can be full. So here we introduce a new thing. It's called like spatial, not a new thing, it's like the terms that already exist, but like we not just interested in soundness. Like again, previously Nova made you be able to fold things that is just like complete of three things here. But now we want to generalize it, like Protostar want to generalize it so that it can fold the things called spatial soundness protocol. So now instead of like folding R1CS stuff, we can fold anything that is like this thing, which is like more general things. And what does it mean by like spatial soundness, right? So basically like if you look at soundness definition, it means that extractor can, given a valid proof, extractor can extract a valid witness. Then spatial means that like extractor cannot just find it, extract by witness. It is bigger than that. So basically like this thing is more general, which means that it is based on stronger assumption, right? Stronger assumption. So instead of like extractor can just don't have any information, they can just like extract witness out of the valid proof. Here, extractor need the things called like history tree. This is like not exactly the term, but basically it's like the tree of transcript. So in normal soundness, extractor is pretty good, like it can just like extract it out of nowhere, but not here. It actually needs another things called like the tree of the transcript of the interaction, which means that like yeah, it is based on stronger assumption, it is more general protocol. And yeah, I think like just to give more pictures, like what does it mean by like history tree or whatever, like so yeah, like every time like prover interaction with the verifier, right? Yeah, let's say prover do something, they have witness, of course, which is again, this spatial soundness has nothing to do with zero knowledge. Like it's just literally like this part, which is more like relaxed thing, right? So it doesn't mean that it has to like have private witness or whatever, it doesn't care. So in normal interaction, like let's say prover sends something to a verifier and then verifier sends some like random R, right? Like random R. And then prover think of something and then they send back and forth. This is like normal like interaction like protocol, right? But then when we mean by history tree, we mean that like we give more information to extractor so that it can extract the witness. Which means that basically, like look at this, like this is just a random R, right? But then it can be R1, it can be R2, it can be R3, it can be like any like things that is possible that the verifier like choose randomly for us, right? And when we mean by history tree, we mean that like let's say the prover start with M. If the verifier send out R1, let's say it's R1, right? The prover will do some calculation and send out back M of R1, let's say. So it will be M of R1 now. But if M send R2, it's R2, right? Let's say if M send R2, prover will like compute stuff and they will send back M R2. So like it's pretty much like history tree because it's just like hypothetical like situation that like what if like we know like some like outcome of like different R, which in reality like verifier just send once and done. But now here we just like have, again, this is like really general protocol. So like if we have this kind of like knowledge, we can prove of the valid witness. And again, I think this is a bit like theoretical, and how does that matter, right? The thing that matters because we can show that most of the structure, like it doesn't need to be R1CS, it doesn't need to be like specifically Plonk. Like with this like construction, we can create any like a lot of statements that we're interested in. One of that is the things called, let's say you want to prove that some like gate satisfaction, right? Like let's say in R1CS, like you need to do like this thing, right? That's actually right before like this stuff, right? And it involves a lot of things, like weird things and those stuff. But here, like this is really simple. Like basically you have prover and verifier, and there's, let's say this is witness. I mean, C is like public and witness like private or whatever, right? Like again, this is just the general protocol. It doesn't need to be zero knowledge. So if prover want to prove that they know witness that satisfy this thing, how? The stupidest and easiest way is they literally send witness to them. And this actually satisfies this thing, which means it can be false. So it doesn't need to construct any zero knowledge or whatever R1CS structure done. It just like literally say, cool, we have a protocol and you can extract witness given the history tree, even though like here they don't need a history tree or whatever, like they just literally send the view and then verify, just like, okay, cool, I saw your witness, let me check, cool, then done. It means that like, this is like rigid, like spatial sound protocol. It means it can be false. And again, I think if you look carefully, this thing is kind of simplify a lot of things, like, which means that like, if the verifier verify anything that is algebraic, which is like algebra, like this is algebra, like verify is equal, or those stuff, like it can be false. So anything that is like algebraic, like verifier can be false. Yeah, so that cover like our CS of song each, like, so this also means that like the gates can be any degree, like it doesn't need to be like just R1 CS degree, like it doesn't need to be 2, it can be like yeah, like x squared 3, like those stuff, like this is algebraic, it can be verified like once and for all. Quickly things, one more thing is that like lookup. Lookup is tricky because it's not algebraic, which means that like it cannot like easily like see as an equation stuff, but basically like in paper, and not even in paper, it's like a lot more like we can prove that the lookup is 2L plus T spatial out. This is just quickly think, this is just the table of lookup table, number of like row in lookup table. This is just the number of things you want to look up for. Things you want to look up. And these like things in front of spatial soundness, do you remember like that we need history tree, like they may be like different that is like hypothetical. This just means that like if you have the tree that has like 2L plus T value of randomness of R, and it's following a transcript, it can extract witness. So yeah, pretty much like, again, it's generalized, and I think that I want to make this first clear, like it can for anything that is spatial soundness for the protocol, not just zero knowledge. And yeah, lookup or even like those like arbitrarily like number of degree grade can be easily for. Yeah, so I think that's the first part. Again, to not make this talk too long, I think I will skip some. And like again, if you think this way, right, it's a lot more generalized than the like do you remember like when the Nova things, right, like this thing. And then you like put this one into like become like this, right, like you put like try to fold them together or those stuff, right? Like this thing also still be the same, but again it's like generalized, it doesn't need to be this exact equation. But we have to admit that the things that is getting let's see. So we have protocol now, right? The Protostar, again, just construct from this SPS protocol. And then when we want to create Protostar, it means that like we have SPS protocol. Like again, the protocol can be just prover and verifier. Just send like whatever. Again, this is not need to be serial knowledge. It doesn't need to be even non-interactive. It's fine. But again, like usually, you don't want to just send like message long, right? So you want to send it in a commit way. So if you read in the paper, this is pretty much like in introduction, but I think it's the most important like graph to see how like Protostar is actually created from scratch. So yeah, we have commit, we have like commit version of this like SPS protocol, which means that like instead of like this M1, R1, M2, R2 stuff, right? You just become like cool, I send like commitment of M1, and yeah, this guy send R1 back, I send like commitment of M2. It's like yeah, similarly, and at the end you just like send M and just open the commitment, right, to make it shorter. Yeah, and then again, like as we usually love about non-interaction stuff, you can make it become like Fiat-Shamir, right? Like Fiat-Shamir. To make it like not like back and forth, like so it's really this thing, but make it like you know how to calculate R, like hash of the previous transcript, like let's say this thing. All this stuff. So yeah, we have this protocol that we want to follow. We make it into commit version to save things around like communication. We make it Fiat-Shamir to make it non-interactive. And then this is where Nova comes in. Like if you look like this thing, we have like Fiat-Shamir version of this. We just use it as a folding. And when we mean folding, you remember like when she talked about even for who talk about like that we have like E. We have like x and those stuff, right? And we just update like e equal to like e1 plus rt, right? Like rt, and this thing needs to be like compute like pretty long, blah blah blah, right? And yeah, like from this point forward, it's just pretty much the same thing. You have accumulation, and if you want to do IVC, you just wrap this like folding and prover together and have like IVC prover, verifier, blah blah blah, right? So yeah, again, the core is generalizing. One more point that I want to cover about Protostar is that besides it can generate what came before, it also optimizes the thing called cost term. So the second thing that Protostar is like good for is the I would say like optimize cost term. So yeah, just two things. I think like that's a pretty breakthrough. Again, the general things, the general statement, and then another thing is the optimized cross term. What is like optimized cross term or whatever is that, right? To revisit what NOVA is, what is it? Yeah, again, like this, like if in paper it looks a lot uglier because they try to generalize everything. Like, but again, if you remember NOVA, I mean I wrote as well, so I have to look. Yeah, like you remember when folding, like again, we're at this stage. We are folding, we put like E, and E is the like this thing, right? Like yeah. And when you're folding, let's say you need like if you family like something like this, right? A square, E2, and R is just random. E is just the error term of the things that you want to fold together. And this thing is again just commitment, like the bar ahead on top of it is commitment. And yeah, if you look at this, what is this? This is T. And what is even T? So basically T is the things that like we need to, the prover need to calculate. Like in case of NOVA is like this is like B sub 2, like A sub 2, like all this stuff. And actually, like where does this things come from? Basically it's come from things called like multiplication, which is basically cross term. Like if you look at like we want to be able to fold into these things, right? But again, if you just like put like set 1 plus R set 2 and then times like B set 1 plus R set 2, like if you want to do like these things and you like do it right, it will become like so basically like we want to make these things become something just like A, like new C, right? Let's say new C, B new C. But then like there would be a lot of cross term. Like let's say like this thing times this thing, it means that they have like the new pair, like they have the cross term. And this thing even get worse. Like if let's think of like this is just like quadratic, right? It's just like C plus something plus D or something, which means that like you just care about like this thing. But then the cross term comes. And when cross term comes, it means that you need to calculate these kind of things. And when you need to calculate this kind of thing, you need to like do this like multiplication, the long one, like those stuff, right? And yeah, things get worse when we want to do any arbitrary like degree. Like again, obviously it's just quadratic, it's not bad. But again, if we want to do something like to the third, right? Let's say we want to do like verify that, let's say like x to the third, like let's say you want something like this, right? And then you want to fold. When you want to fold, you mean that like you want to put this with like x1 plus r x2 stuff, right? And then yeah, like here you go. You have like a lot of like this like this like these kind of things that you don't really prefer of. And if you imagine like if it's not 3, if it's 4, it's just you have like a lot of cross term. And when you have cross term, like you mean that like you need to commit. Like the prover itself needs to commit the E. Like this thing. They have to calculate, they have to commit. So the more like degree you have, the more like this like blow up things that happen. So this thing makes like, even though yeah we support like degree n gate, it is not really like good because like every time you like multiply by more n, it's just like more cross term, and non cross term means more like values that you need to like commit polynomial form, and that sucks. So how do we solve that? So yeah, this is where Protostar help save the world a bit. So the way we solve it, so instead of again like let's say we net cross term, right, and we need to verify those like commitment. So instead of like this is similar to most how our trick is done, right? So if I put things, let's say your degrees, and yeah, this doesn't really matter anymore. So let's say we have degree decade. And degree decade means that like we have like d minus 1 cross term, like right, because like if it's 2 it's like x squared plus like 2xy plus y squared, this is cross term. Like if it's 3 it's like x squared y squared x, like this is like degree 3 you have like 2 cross term, degree 2 you have 1, yeah. So basically if you have degree decade you have like d minus 1 cross term. And yeah, you have d minus 1 cross term, and then yeah, let's say you have like L gates, right? You have L equation to check. So you have L equations, and at each equation you have like d minus 1. This is like 1 to a d minus 1, and this is equation 1, right? Which is the gate, right? The equation just like determine the gate, and equation 2, this is all the same, d minus 1 and to the L, right? So how do you actually like do this stuff? Like normally again we need to like do the commitment, which costs like d minus 1, like you just commit like d times, right? D minus 1 times. Then like this one is equal to 0 anyway. So instead of like manually like verifying these like commitment things, why don't we just put like we know how to do it, right? Like let's say this, I call it equation 1, equation 2, equation L, right? Instead of verify equation 1 is 0, equation 2 is 0, we did the same thing that we usually do. So basically you have equation 1 and you just plus with random things, R1 equation 2 plus R2 equation 3, right? Like this stuff. So basically you just like linear, like random linear combination them together so that you can verify at once. Yeah, that's good, But again, we have L equation, this means that we need to have like L of R, but that's still a lot, right? Like prover needs to provide like a lot, like L. So instead of doing like R1, R2 and stuff, right? What if we can oh, I shouldn't really read this. That's really here. So yeah, instead of that, why don't we just do just one random number? So let's say call R, right? And then this is pretty much the same, like R squared equal 3 goes down to the L minus 1 equal. Yeah, and just prove that this is 0. Again, this still requires the prover to send what? The prover just send all this stuff, right? And then the verifier need to verify that it is actually like this, like multiple things. So basically, yeah, the Protostar try to not just verify like L equations, but they try to condense it together. And I think another cool tricks that they do is that instead of just send like doing like R squared until like R minus 1, they actually send like two things. Yeah, this is pretty weird, but basically they send the things called like beta and gamma. So beta, like beta 1 is like R, beta 2 is R squared, beta 3 is R3, blah blah blah, until beta square root of L minus 1. And then gamma 1 is square root L, yeah, gamma 2 is r to the 2 square root L. Sorry, this is square root L. So basically, instead of like sending like L terms, right? This is L term or L minus 1, like yeah, it's really close, right? L terms. Instead, they just send 2 root L terms because there's root L of this, there's square root L of this, and basically like with this thing, you can combine like any combination to create all of this stuff. So it saves even more. Like it just don't send L terms, it just send like 2 root L terms. So yeah, basically this thing is another core thing of the Protostar thing. So they optimize the cross term, they just get rid of the L equation. They make sure they put it together to verify just one, and then they optimize even more, not just like sending this like random like L term. Oops, sorry. Thank you. But yeah, they send like 2 root L term. So let's recap a bit how this like matters, right? Like how, and again, I think if you guys a bit like lost, these things happens. Like remember last time, like that we have like prover, verifiers, and they have like interactions, right? Like at this stage, right? Again, like this is the thing that came before. We commit, we make fierce Shamir, and this is just like folding Nova, and then like last one is like IVC or whatever, right? But again, if you read Protostar paper, they don't take care about like IVC at all. They just emphasize on like this thing and this optimized thing, and the accumulation is pretty much like the same as Nova. But again, the syntax is pretty bad. But yeah, basically, where does this happen? Like where does this optimized thing happen? It doesn't. So basically, yeah, the prover verifier in this state, the first earlier one just talk to each other, and then verifier verify something, right? It is in this part that like they need to verify that something is like, this is where the verify of that L equation happens, right? So instead of like doing L equation, again, we will send like beta and gamma here, and then verify, we just need to verify one equations. So this thing is called compress. This thing compress the cost here. It happens here. SPS protocol, compress. SPS protocol. And then after compress, yeah, commit, fierce Shamir, folding, and IVC. So yeah, let's take a last step to see how these things helps accelerate or like save the cost stuff, right? So before, let's say let's move up. So before compress and after compress, right? So yeah, number of equation before compress is of course L, after compress just 1, and 2 plus L, and 2 versus L. And the reason this happened because we still need to verify, right, that like each step of like this, because like that's like root L term of this, right, root L term of this. But we still need to verify that like, let's say like V2 is still, beta 2 is still like V1 times like or something like this. Like they still need to verify this thing, but this is trivial. It's like pretty cute, like complete equation to check basically. So yeah, this is like things going, but the core thing is that like yeah, it's from L to like just root L. Then the degrees of equation, right? So the degree of equation, basically this is D, right? Because at first it's D, but then at like after compress, right? Again we have to multiply this thing together to construct like the exponent of R, right? So the degree just add on by 2. So it will be just D plus 2. But again, this is just one equation, right? But this is just like L equation, but yeah, the degree increase a bit. And yeah, this thing degree just, yeah, negligible, is very small anyway. The cross term, again, the cross term things, this is just like, there's the minus 1 cross term, is the L equation. But here it's just like one equation, right? So the cross term is like D plus 1, right? D plus 2 minus 1, which is D plus 1. And yeah, you can count this cute small thing is like cross term. And yeah, I think the core thing is that the commitment cost. So basically the commitment cost, before this there's a D minus 1, right? And there's an L. So basically if you commit like this thing, you just like one like commitment here, right? And then basically you have D minus 1, so you just have to like D minus 1 commitment, like MSM of length L. Again, if you compress it off, you compress to one equation, right? And though basically you just can send that as a plain text. Like you don't need to commit, like you don't need to like commitment that together because you don't have like L rows. But again, like, you just still have to like commit like this like square root L thingy, right? But again, just one, like just one. So just one MSM. Yeah, this is really like start different because like again earlier like if the gate degree is so complex, if you just blow up, but here it's just one. And yeah, I think yeah that's pretty much it. I think the size is not that different, but yeah. So again, I think the emphasize thing that made me at first I'm confused a little, right? Because if you read Protostar, this part will look really big. But again, it's just literally the same, almost the same as Nova, but it's just like more general terms. But I think the key is that to realize that is that the fact that they can for any like spatial sound protocol, and they optimize the cost term. Pretty much that's it. And this thing is just make notation more general, but just get you confused, I guess. So yeah, me too. Thank you.
Okay, first question. How many hours did you spend on the reading that paper? How much hours?
I used to skim a bit when I helped doing the axiom things, but yeah, I've never. I don't know. Wait, let's see.
More than 2 days or more than 1 week or?
I think around 2 days.
Around 2 days.
2 3 days, yeah.
Okay. Okay, fantastic.